Okay, here we are back again. We've learnt about trees and how to use trees in R, and now we're going to see how to use trees in the context of random forests and boosting. And we'll see this gives us pretty powerful predictors. So there's two packages, random forests and boost, and GBM, which does boosting. We'll start off with random forests. So as we know, random forests will actually build lots of trees and then average them and reduce the variance of bushy trees by averaging. So we load the random forest package, and we're going to use the Boston housing data again, and that's in the mass package, so we'll get that up. We'll set a random seed, and let's have a look. We see we got 506 observations in the Boston housing data. And we're going to make a training set of size 300, so we'll use the same construct as we used before, and we've got indexes for training. Let's just look at the Boston housing data, so we can run a help query on that, and we see it's the 506 suburbs of Boston, and for each suburb we've got demographics and things like crime per capita, types of industry, average number of rooms per dwelling, average proportion, the age of the houses, and various things. And what we're going to use as a response is the median value of owner-occupied homes for each of these counties, for each of these suburbs. Okay, so it's a data set that's been around. It was based on the 1970 census in Boston. Okay, so we'll start off with a random forest, and it's the same kind of strong construct as before. The response is med-v, median value, and to be modeled as dot, which means as a function of all the other variables. And we want to use the train subset, and very fast random forests, and we can just print out the random forest. It gives us a summary. And it tells us the number of trees. So that was 500 trees were grown, and they're bushy trees, each of them. So as you can see, that was pretty fast. And it gives you a summary of the fit. It gives you a mean squared residual and the percentage variance explained. And when we studied random forests in the notes, we talked about the out-of-bag error. So these are out-of-bag mean squared residuals. So each observation was predicted using the average of trees that didn't include it. So these are sort of de-biased estimates of prediction error. So one of the pretty much only tuning parameter in a random forest is the variable called mtry, the argument called mtry, which is the number of variables that are selected at each split of each tree when you come to make a split. So if mtry, for example, is 4, of the 13 variables in the Boston housing data, 4 are selected at random. Each time you come to split a node, 4 would be selected at random, and then the split would be confined to one of those 4 variables. And so that's how random forests decorrelates the trees. So what we're going to do is we're going to fit a series of random forests. There are 13 variables, so we're going to have mtry range through the values 1 to 13, and then we're going to record the errors. And so we set up 2 variables to do the recording of the errors, and then we go in a loop for mtry in 1 to 13. We're going to fit the random forest with that value of mtry, and here we'll just restrict the number of trees to be 400 for no good reason, except that 400 is sufficient here. And we give mtry as an argument, and of course it's fit on the training data. And we can straight away plug in, extract the mean squared error, because that's out-of-bag error. That's on the object, so we do that. And then we predict on the test data, so there's Boston minus train, and passed as the data in the argument to predict, and fit being the fit of the random forest. And then we compute the test error. So there's our with construction again, Boston minus train, and we compute the mean squared error, so it's mean of med-v minus pred squared. Med-v will be picked off the data frame Boston minus train. So these commands, we're still in the loop, so it's not actually executed. And then we'll just, in case it takes long, we'll print out the value of mtry as it's going. Okay, so here we go. And look how fast that is. So it's 13 times 400 trees have been grown here, and it's done. And now we can make a plot. And so we actually use a matplot command because we've got two columns. We've got test.error and outofbag.error, oob.error. So we C-bind them together to make a two-column matrix, and then we make a single plot with matplot. And you can see we put some other arguments in the matrix. We told it to use plotting character 19, which I like. We gave two colors, red and blue, and type equals B means type equals both, means it plots both points and connects them with lines. And we gave a ylab, mean squared error. And we can put a legend in the top right corner, and we see the red points are out of bag and the blue points are test error. Now, ideally, those two curves should line up pretty much, and it seems like the test error is a bit lower. But be warned, there's a lot of variability in these test error estimates. And so since the out of bag was computed on one data set and the test error on a different data set, and they weren't very large, these differences are pretty much well within the standard errors. And don't get fooled by the fact that the red curve is smoothly above the blue curve. These error estimates are very correlated because the random forest with mtry equals 4 is very similar to the one with mtry equals 5. And so, so that's why these curves are, each of the curves is quite smooth. Okay, what we do see is that mtry around 4 seems to be about the best, at least for the test error. For the out of bag error, around about 8. So somewhere in the middle. It's quite a flat plateau there, and with very little. With very few tiers, we've fit a very powerful prediction model. This is the random forest here, and got pretty good performance. Just as a point, 2 points to note here. On the left-hand side is a performance of a single tree. So this will be a bushy tree, but that's a performance of a single bushy tree. And the mean squared error on the out of bag is 26, and we drop down to about just over 14 here. So it's just a little bit above half. So we reduced the error by half, and likewise for the test error. These errors are somewhat different, but by using a random forest. And on the right-hand side here, we use all 13 variables. So this is actually bag-in, which was random forests and bag-in were due to Leo Breiman. Bag-in came out earlier, and random forests were a later enhancement. And so these are all produced using the random forest function in R. Now, random forest, as we learned in the course notes and lectures, random forest reduce the variance of the trees by averaging. So it grows big bushy trees and then gets rid of the variance by averaging. Boosting, on the other hand, is really going after bias. And so boosting grows smaller, stubbier trees and then goes at the bias. So we use the package GBM, Gradient Boosted Machines, in R. So we load up that package, and we're going to use the same data set here. And so there we give a call to GBM, pretty much the same as the call to random forest. GBM asks for the distribution, which is Gaussian, because we're doing squared error loss. We're going to ask GBM for 10,000 trees, which sounds like a lot, but these are going to be shallow trees, and that's given by interaction depth. So interaction depth is the number of splits. So we're going to say we only want 4 splits in each of the trees. So it'll do best first split in, and it'll stop it after 4 splits. And then shrinkage is 0.01, so that's how much we're going to shrink the trees back. So I just chose these parameters. One would normally fiddle around with these parameters to decide which to use. And so here's Jeep. Wow, look at that. 10,000 trees fit in a few seconds. So we can do a summary. And what summary does is it actually gives a variable importance plot. And there's 2 variables that seem to be the most important. There's the number of rooms, and the second variable is LStat, which is the percentage of lower status economic status people in the community. And so those are the two most important variables. But they aren't all labeled in this plot here because of the font size we're using. If we reduce the font size, we would have seen them all labeled. So the variable importance plot is a good way of seeing. It seems like these two variables are by far the most important, and then the other variables play a lesser role. We can do partial dependence plots. So let's plot these top two variables. And so this shows us, it's kind of a roughly relationship, but it shows us that the higher the proportion of lower status people in the suburb, the lower the value of the housing prices. Not a big surprise there. And reversed relationship with the number of rooms. The average number of rooms in the house increases, the price increases. So no big surprises there. Okay, so what we're going to end off the session by predicting our boosted model on the test data set. Normally one would use cross-validation in boosting to select the number of trees. We won't do that here. We'll leave that up to you to do. You'd have to run the cross-validation yourself. And in fact, these other tuning parameters, like the shrinkage parameter, is a tuning parameter. One would probably use cross-validation to select that as well. And so there's a little bit more work and fiddly stuff to be done with boosting over random forest, but often it's worth it. So what we'll do here is we'll just look at the test performance as a function of the number of trees. And so we make a grid of number of trees in steps of 100 from 100 to 10,000 by, okay, so we use seek to do that. And then we run the predict function on the boosted model, and it takes n.trees as an argument. And so it was pretty quick, and it's produced a matrix of predictions on the test data. There are 206 test observations, and you see we got 100 different predict vectors at those 100 different values of tree. And so then we compute the test error for each of those. And we use the apply function. So we use our with command again, and we use the apply function. And now predmat's a matrix, but medv is a vector. And so this just recycles as vectors. So that's a little bit of trickery that I often use in R. It's handy. So that recycles it. So this is actually a matrix of differences. And then we apply to the columns of these squared differences the mean. And so that'll compute the column-wise mean squared error for these guys. And it did that, and then we'll make a plot, and we see the boosting error plot, and it pretty much drops down, and drops down lower, it looks like, than the random forest. This is a function of the number of trees, and then seems to level off, and it doesn't appear to be increasing. If you really ramped up the number of trees to a much bigger number, it would slowly start to increase. But this is evidence of the claim that boosting is reluctant to overfit, and it certainly seems to be the case here. If we go back and replot our random forest performance, so here we go. And now we can go back and include our boosted results in that plot. We see it's doing about, no, that's not what I wanted. Okay, I did the wrong plot. So there's our, what I'm intended to do was, there's our boosted plot, and I'm going to include the best test error from the random forest over there. So there we go. And we see that boosting actually got a reasonable amount below the test error for the random forest. Okay, so there we have it. Random forests and boosting, two powerful methods. Our experience is that boosting, especially if you're willing to go through the tweaking and the tuning, will usually outperform random forests, but random forests are really dead easy. They won't overfit. The only tuning parameter is the M-try, but the number of, when I say they won't overfit, by increasing the number of trees in random forests, it won't overfit. It'll just, once it stabilizes, it's stabilized, and adding more trees doesn't make much difference. With boosting, not the case. You've got genuine tuning parameters, the number of trees, the shrinkage parameter, and the depth, but both very powerful methods.